Hi everyone, in this video I'll be going over 10.3. We're getting into logarithms. So there's this strong connection between exponential functions, which we saw previously, and these new functions called logarithms. And the most important connection is the fact that the exponential function and the logarithmic function are inverses of one another. So we're going to be able to solve a lot more equations now that we have this inverse function to the exponential function. So you can kind of get out of situations, kind of like if you're driving and you have drive and reverse. Sometimes if you get up against the wall and you only have drive, then you can't get out of that problem. You can't solve that problem until you install this inverse function, the reverse gear. And now once you have that reverse gear, you can pop it into reverse and you can solve that problem of being up against that wall. The logarithm is kind of like our reverse gear, where the exponential function is kind of like drive. So we're going to be able to solve certain problems now that this inverse function is being introduced. So all exponential functions are 1-to-1. So that means that all exponential functions have inverses. And as I was saying, the logarithm is that inverse. Here is our general logarithmic function. So we literally have y equals log. So this means logarithm. It's not, these are not variables. But this is meaning I'm taking the logarithm base b of x. This is completely equivalent to b to the y equals x. So there's this logarithmic way of saying something. There's this exponential way of saying something, but actually that's the same meaning. Just different ways of saying that thing. We'll get into this now. So for example 1, it says, write each equation in its equivalent exponential form. So this is now in logarithmic form. So I have y equals 3, I have b equals 7, and I have x equals x. So to get this into the exponential form, well, whatever it's equal to becomes the power on the base. So the base in this case is 7. And then it says whatever it was equal to, which is 3 here, that becomes the power on the 7. So I'll have 3 as the power, and this will now be equal to, so if I was taking the logarithm of x, this is now equal to x. That would be it. That's the exponential form. Let's try another one. So if 2 equals log base b of 25, again, we're just converting. So I'm not solving for b. I'm not solving for x, really. Just converting. So I would have the base b raised to the second power, and this would equal 25. All right, let's go on to page 153. So I'll leave some of these open for you guys. Of course, I'll attach a key. So example 2, it says, write each equation in its equivalent logarithmic form. So just going the reverse direction. So just to remind us, we had y equals log base b of x, and that's completely equivalent to b to the y equals x. So if I have this exponential form, in other words, I'm sitting here, I want to now convert to this logarithmic form. So that base of the exponential becomes the base of the logarithm, right? So whatever b is here becomes the base on the logarithm. Whatever the power was is what the logarithm is equal to. So I'd have 5 equals log base 2 of x. That would be the logarithmic form of this. Just skipping down to part 3. So e to the y, this is a base e. So I'll have a logarithm of base e. So this will be equivalent to y equals log base e of 33. Right? Whatever the exponential was equal to becomes what is called the argument of the logarithm. So maybe I'll just make note of that real quick, those vocabulary words. This is called the argument, whatever is being evaluated. This is called the base. And this is called the value of the logarithm. So with this one, the argument will become 33. So this would be a logarithmic version of that, or we'll see this in a second, you could write y equals the ln of 33. So the reason why that's equivalent is because log base e of x is the same as ln of x. Log base e is so popular, it comes up so often, that it was given its own name. So when you have a logarithm of base e, you can just say natural log of x instead. So, moving on. Now evaluating, we're going to get to kind of what the meaning of a logarithm is now. So if you use your calculator, if you have this type, check out this button over here. So if I want to know what log base 10 of 100 is, I can press this button, type in 10, scroll to the right, press 100, press equals. This is the number 2. So this is equal to 2. But let me explain why. So let's imagine we didn't have the calculator or something like that. So log base 10 of 100, let's just call this some number y. Okay, so let's say we didn't know that this was the number 2. It is the number 2, but let's just say we didn't know what it was and I call it the number y. If I convert this now to exponential form, we would have 10 to the y equals 100. So now can you figure out what y is? So I would need to square 10 to make 100. So this would tell me that y is 2. In other words, this whole thing, since it was equal to y, is equal to 2. So the value of the logarithm, maybe I'll write this here. So it's right here already, but the value, I'll rewrite it, is the power to which the base needs to be raised to equal the argument. Okay, and that's said here a different way. It says evaluating a logarithm amounts to determining the power to which the base needs to be raised to equal the argument. So in other words, the value of this logarithm, in other words, what this equals, is equivalent to the power that you put on the base to equal the argument. Right, this is the number 2 because the power that I put on 10 to make 100 is 2. Let's try another one. Maybe I'll just do this one as well. So log base 3 of 3, again, don't forget about the existence of calculators. So log base 3 of 3, this apparently is the number 1, but let me explain why. So again, imagine that we had log base 3 of 3 equals something, and we didn't know what that something was. If you rearrange this, you would say 3 to the y, and this is rearranged into exponential form, equals 3. So now you can see, yeah, if it's 3 to the first, then I get a solution. That's why this is the number 1. So log base 36, again pressing this button right there, log base 36 of 6, I'm getting a half. So this is a half, but then maybe just another because. So let's just say we didn't know what it was and it's equal to y. Then rearranging this into exponential form, we can write 36 to the y equals 6. So basically I need to take a square root of 36 to get a 6. So y equals a half is the same as a square root. The power 1/2, same as a square root. Here are some important properties down here. So anytime you actually have log base b of b, that'll equal 1. Right, and if you think of that in exponential form, it should make some sense. Right, b to the first would equal 1. If you think of this one in exponential form, it should also make some sense. B to the 0 equals 1. If you think of this in exponential form, you have b to the x equals x. Sorry, b to the x equals b to the x. And I'll leave this one to you to convert into logarithmic form. But you can convert this into logarithmic form. See what you get. So example 4, log base b of b, from that previous property, this should be the number 1. Log base 8 of 1. So if it helps, you can rearrange this and say, all right, let's imagine log base 8 of 1 equals something. Then the exponential version would be 8 to the something equals 1. So that something needs to be 0. So let's move on to graphing. So let's look at a graph of this. Remember that the point plotting method works always. Okay, so that's actually what I'm going to use here, but I'll talk about something else as well. So let's say we had this table for f of x, and then maybe over here I'll do a table for g of x. So maybe I'll pick -2, -1, 0, 1, and 2. So if I plug in -2 into this function, I get 1/9. Plug in -1 into this function, I get 1/3. Plug in 0 into this function, I get 1. Plug in 1, I get a 3. Plug in 2, I get a 9. Okay, so I'll go ahead and plot those. So at -2, we're just above 0. Just do your best. -1, we're at a 1/3. 0, we're at 1. 1, we're at 3. And 2, we're at 9. So we get this exponential curve, which does not come down here ever. It just gets closer and closer to 0. For g, I'm actually going to do something weird. I'm going to pick 1/9 as an x. I'm going to pick 1/3 as an x. I'm going to pick 1, 3, and 9. Okay? So plug in 1/9. So log base 3 of 1/9. Log base 3, 1/9. This is -2. log base 3 of 1/3. Let's try that. That's -1. Log base 3 of 1, that should be 0, right? Log base anything of 1 is 0. Log base 3 of 3, that's a 1, because the power I put on the base 3 to make a 3 is a 1. Log base 3 of 9 is 2, because the power I put on the base 3 to make a 9 is a 2. So I'll plot these now. So we have 1/9 for x and then -2. So it's somewhere down here. We have 1/3 for x and then -1 right about here. 1, 0, 3, 1, 9, 2. Okay. Something to note is that these appear to be symmetric across this line, y equals x, which means that these two, f and g, are actually inverses of one another. And if you look at the table, notice that when we had -2 1/9, we got the exact opposite here, 1/9 -2. When I had -1 1/3, I got 1/3 -1. Everything just flipped. So if you can verify that the functions you're graphing are inverses, then you can just flip all these points and you know that you're graphing and you're finding good ordered pairs for both. If that doesn't make sense to you, then you can just pick different x's and use the point plotting method here, just the same. So what about domain? As you maybe saw from here, the logarithm, the light blue, does not encroach on negative x values. It doesn't even hit 0. Might be hard to tell from my graph, but it will never hit 0 exactly. So for logarithms, when there's a function inside of here, we need that function is strictly greater than 0, and that'll define the domain. So our function here is x minus 6. I guess I'm doing both of these. So I would need to figure out when x minus 6 is strictly greater than 0, and this will be the domain. So I'll add 6, add 6. I have x needs to be greater than 6. So I'll state this in interval notation maybe. So 6 to infinity. That would be the domain. For the next one, we're looking for when x plus 10 is strictly greater than 0. Subtract 10. So I'm getting that x needs to be greater than -10. So I'd have -10 using parentheses, because it needs to be strictly greater than, and then towards infinity. Okay, so some applications. We have that this decibel scale. So you may have heard of decibels from the intensity of sound. So when you're got your earbuds in, depending on what volume you select, there's a certain amount of power coming out of those headphones and into your ears. And that scale that measures that power, the intensity of that sound, is this decibel scale. There's also an application involving logarithms with respect to this Richter scale. So this is our decibel level formula, by the way. Down here is our Richter scale formula. So you may have heard of earthquakes like, oh, that's a 7.2 on the Richter scale. And that'll describe the intensity of the earthquake. So the higher that number is, the more intense the earthquake is. So both of these are examples of when logarithms are actually used to calculate things that we care about. So let's do an example. Let's say we had this problem. So extended exposure to noise that measures 86 decibels can cause permanent damage to the inner ear, which can result in hearing loss. What is the decibel level of music coming through earphones with intensity of 10 to the negative 2 watts per square inch? Okay, so it said that the decibel level, if I just reference it, it's 10 times log, and it doesn't have a base on it. If it doesn't have a base on it, then it's implied to be a base 10 logarithm. Same with here. This is a base 10 logarithm. If it's not written and it says log, then it's implied to be base 10. So this is 10 log of the intensity divided by 10 to the negative 12. If you're wondering about that 10 to the negative 12, that's barely perceptible to the human ear. So we're dividing that into the intensity and seeing how many times that happens. So extended exposure, what is the decibel level of music coming from earphones with intensity of 10 to the negative 2? So for that, I just need to plug in 10 to the negative 2 into the intensity. So I'll have D equals 10 times log, and that's a base 10. You can write it if you want, of 10 to the negative 2 divided by 10 to the negative 12. So I'm going to type that in. So 10 times, so this button here, by the way, notice how it doesn't have a base. This one does. This one is implied to be base 10. So I can use it and just say 10 raised to the negative 2 divided by 10 raised to the negative 12. So this would be 100 decibels. So you wouldn't want to have your headphones on that intense for too long. Maybe I'll talk about example 9 also. So in 2014, Chile experienced an intense earthquake with magnitude of 8.2 on the Richter scale. In 2014, Los Angeles also experienced an earthquake which measured 5.1 on the Richter scale. Compare the intensities of these two earthquakes. So we have this Chilean one, which was 8.2, so I'd have 8.2 equals, and by the way, that was just r equals log of I. So I'd have 8.2 equals log of I. For the LA one, we'd have 5.1 equals log of I. So I would want to solve for I here. Okay? So one way of doing that is, I know that these are log base 10, is to rewrite these in exponential form. Okay? So 8.2 equals log base 10 of I. I'm going to rewrite that into exponential form. So I would say 10 to the 8.2 equals I. So what I'm using there is the fact that if you have y equals log base b of x, that translates to b to the y equals x. So I'm just using that same thing that we started this video with and applying it here. So this would be the intensity of the Chilean. For the LA one, we had 5.1 equals log base 10 of I, and that would transfer to 10 to the 5.1 equals I. by compare the intensities, what I really mean is like how much more powerful, how many times more powerful was the Chilean earthquake than the LA one. So to figure that out, I can take 10 to the 8.2 and divide by 10 to the 5.1. So it was about 1,258 times more powerful. So the Chilean Okay. Moving on. Time to solve some logarithmic equations. So I'm going down to example 11. So as I said, often to solve these, you can use that property of converting between logarithmic and exponential. So I'll use that here. So I'll just write it down for us to reference. So if I have this logarithmic way of saying this, I can convert it. It must be 2 to the 4th equals 3x minus 5. So as soon as you convert this logarithmic equation into this exponential form, you now actually just have a linear equation. So 2 to the 4th would be 16. And now solve for x. So 21 equals 3x, divide by 3. So 7 equals x. And you can definitely check that, and you do want to check these. So I'm going to make sure. So I'll need this button right here. So I'll go log base 2 of 3 times 7 minus 5, and I'm waiting for a 4. So that looks good. ln of e to the 2x. Okay. So one thing you can do is rewrite this as log base e of e to the 2x equals 4. Log base e of e to the 2x. So these actually completely cancel. Just to remind you guys, there's this property over here. So when you have log base b of the same base raised to whatever, just the whatever is left. So log base e of e to the 2x is just going to leave 2x. So those cancel, and I just get 2x equals 4, and then divide by 2. X equals 2, and you can definitely check just to make sure. So plugging in, so this button, by the way, find a place. So this button is your log base e. That's your natural logarithm button. So you can go ln of shift ln to get the e raised to the 2 times 2. This should be equal to 4. Cool. Okay, Please check the key for the solutions to the rest of them. Talk to you next time. Bye.